All right, good afternoon. Um, just kind of going back to exponential and logarithmic functions and just some things I just want to stress, and I'm going to give some visuals in just a moment. Again, from the other day, okay, we had y is equal to f of x is equal to a to the x. And again, for the exponential base a, okay, that is a positive value excluding 1, however, and concerning the domain and the range. Now, again, y has to be positive, so the range will be positive values. And for x, there's no restriction on x in the case of an exponential function. X could be 0, it could be positive, it could be negative. So we have all real numbers x that would define the domain. Okay, so we have with the exponential function y is equal to a to the x. Again, you had the domain, that is the x values will be the set of all real numbers, and for the y values, okay, we're looking at the range to be positive values. And again, by definition, a logarithm is going to be the inverse of an exponential function. So just kind of going back to what we had, transitioning from y is equal to a to the x to its inverse. And again, just like with one-to-one functions and their inverses, so I'm going with the implicit notations, interchanging x and y, for upon I have x is equal to a to the y, and converting again to y from a is equal to y. And again, you take care of exponential bases upon applying logarithms in the matching base. In this case, we have a base a logarithm on both sides, and this leads up ultimately to y is equal to the inverse of f of x is equal to the base a logarithm of x. And once again, an exponential function is 1-to-1, and the x and the y values, once you switch around, will define, okay, the domains and the ranges of the inverse. Okay, so in the inverse, in this case for the logarithmic function, the domain is going to be positive values in x, and in the case of y, okay, we have all real values. Okay, so again, the between the exponential and the logarithmic function, the domain in one is going to be the range in the other, and vice versa. And to give you just a bit of an item, and this is perhaps more for like just some of the Alex items, okay, involving exponential functions and logarithms, and just to show you just some of the dynamics that will play out. Okay, like if you have some added components in the mix, and let's say if you're looking for the domains and the ranges of the given function as well as the inverse, and we'll say that we have for y is equal to f of x is equal to 3 raised to the x. Okay, now for what we have in the case of this function, let's go ahead and state the domain. Okay, so we have for the domain, okay, for the domain, okay, so we have x, we have in position as 3 to the x. X could be any negative, 0, or positive real value. And so the domain, it had to be the set of all real numbers. Now for what we have in the case of the range, okay, like if you took a number 3, like you took it to like to the negative 17, it'd be a very small positive decimal number. And the more you make x to be negative, you're just going to make 3 to the x into a very small positive number. And if you make x into a large positive number, we would have like 3 to the x approaching infinity. So the range, again, we will have values of y that will be greater than 0. And if we look for the inverse, again, so we have starting out for y is equal to 3 to the x. And if I look at, again, interchanging x and y, so we have in the setup, okay, so we have x is equal to 3 to the y, okay. And again, to convert from 3 to the y to just y, again, I take care of exponential bases by applying logarithms in the same base. So I'm going to be taking the base 3 logarithm of both sides. So we have the base 3 logarithm of x is equal to the base 3 logarithm of 3 to the y, and that is going to go to y. So we're going to have that y is equal to the base 3 logarithm of x. And so we're going to have that y, in this case, is going to be equal to the inverse of f of x. Again, which is going to be the base 3 logarithm of x. And for this inverse function, okay, now the domain, and just kind of taking from the page of what we have for the range in the exponential function, okay, for the base 3 logarithm of x, the domain is going to be positive values in x. Now for what we have in the case of the range, okay, again, we had all real numbers for x in the exponential, and guess what? We have all real values for y in the range. And just looking at what we have, just kind of looking at what we have in the case of taking what we have, let's see where the okay, let's see, 3 to the x. I got that one. I want one with just the graph itself. Ah, there we go. Okay, so just looking at what we have in the mix. Okay, so you have f of x is equal to 3 to the x. Okay, and so you're going to have this graph in red. Okay, and if you notice, you have like with x at 0, 1, and 2, like 3 to the 0 is equal to 1. Again, a non-zero number to the 0 power is equal to 1. With x at 1, okay, we have 3 to the first is equal to 3. And with x at 2, 3 to the second is equal to 9. So I have these ordered pairs. So I got 0, 1, 1, 3, and 2, 9. And then for the inverse, with the base 3 logarithm of x, so if I interchange the x and y values, so for x at 1 and 3 and 9, the respective values in y will be 0, 1, and 2. And so again, have interchanging x and y values between the exponential function and the logarithmic counterpart. And both of these graphs will reflect each other about the line y is equal to x. All right. Now, and looking at what we have for the next item, and this is going to be almost a duplication, but there's going to be the slightest change. And this is going to be where we have we'll say we have y is equal to f of x. is equal to 3 to the x minus 1. Okay, now we still have x as the exponent or power to which 3 is going to be raised. So you're still going to have the domain to be the set of all real numbers. Now in the case of the range, okay, notice before whenever we had 3 to the x, now I'm just going to kind of mention here for 3 to the x, notice you have like for 3 to the x, notice as x gets smaller and smaller and smaller and smaller and smaller. Okay, it's tangent, but it never goes underneath the x-axis. So you can say that as x gets smaller and smaller, we're going to have 3 to the x is going to be just like the smallest imaginable positive number there exists. But let's say if I go down 1 unit, well, guess what? Your y value is going to be like almost 0 minus 1. And for what's going to occur is that with the subtraction of 1, your range is actually going to be referring to values of y that will be greater than -1. And in interval notation, we're going to have from those values, okay, going past -1 all the way out to infinity. Now, in looking for the inverse of this function, okay, so I have y is equal to 3 to the x minus 1. And if we look at interchanging x and y, okay, so we're going to have here, we have x is equal to 3 to the y minus 1. Okay, and after the interchange, so I still have y as the power to which 3 is going to be raised. And I'm going to get this term by itself. So I'm going to add 1 to both sides. Okay. Okay, so having adding 1, so I have x plus 1 is equal to 3 to the y. And again, to take care of the exponential base, I'm going to take the base 3 logarithm on both sides here. So I had the base 3 logarithm of the quantity of x plus 1 is equal to the base 3 logarithm of 3 to the y. So we have the base 3 logarithm of x plus 1 is going to be equal to y and just reversing the order, saying y is equal to the base 3 logarithm of x plus 1, and then we have y is equal to the inverse of f of x. And that's going to be equal to the base 3 logarithm of the quantity of x plus 1. Okay, and so we have in the case of the domains and the ranges. So for the logarithmic function, this time we're going to have that x will be greater than -1. And as for the range of the inverse, okay, that is going to be the set of all real numbers. And just looking at what we have now. Okay, so for y is equal to 3 to the x minus 1, if you notice, okay, before with y equal to 3 to the x, okay, this one was just slightly above the diagonal line y is equal to x. But with the downward shift of 1 unit, notice that it comes into contact with y is equal to x, and the inverse rises a bit too, where it also comes into contact with y is equal to x at the origin. And with 3 to the x minus 1, okay, this is what we have occurring. Okay, so we have like at the origin. Okay, now if you think about it, when x is 0, we got 3 to the 0. Now what is a non-zero number to the 0 power equal to? And if you take 1 away from 1, this will go to 0. So we have the origin. Here we have 3 to the first is going to be at 3. Take away 1, we got 2. 3 squared is going to be 9. 9 minus 1 is going to be 8. So we have the origin, 1, 2, and 2, 8. And just switching the coordinates around, this being reference to what we have among the ordered pairs that will make up y is equal to the base 3 logarithm of x plus 1. So we have the origin, now we got 2, 1, and also we have 8, 2 to be in the mix. Okay. Now, and just one other modification, and I'm going to keep this along the lines of the base 3. And if we have, let's say that y is equal to f of x, and we have is equal to 3 to the x, and now we have an upward shift of 5 units. Again, so x is still in the same position, and the domain is going to be the set of all real numbers. And for what we're going to have in the case of the range, notice you have 3 to the x. Now the minimum that 3 to the x alone can be is going to be tangent, but just slightly above 0. But with 5 added, the minimum that y can be is going to be like the smallest possible value that is going to be greater than 5. So the range of the function is going to be expressed symbolically, or in the interval notation, where we have parentheses around 5 and infinity. And just looking at determining the inverse of this function, okay, so we got y is equal to 3 to the x plus 5. And once more, as I interchange x and y, okay, so we have in the initial rewrite, okay, so we're going to have the x is equal to 3 to the y plus 5. And once more, I'm going to get 3 to the y by itself. So I'm moving a different constant this time around. So looking at subtracting 5 on both sides. Okay, so I'm going to have x minus 5 is equal to 3 to the y. And once more, I'm going to take the base 3 logarithm of both sides here. So I have the base 3 logarithm of x minus 5 is equal to the base 3 logarithm of 3 to the y and so I had that y is equal to the base 3 logarithm of the quantity of x minus 5, and just putting back and utilizing inverse notation. So we have the inverse of f of x is equal to the base 3 logarithm of the quantity of x minus 5. Okay. And if you notice, okay, with the domains and the ranges, now with the exponential function, okay, we had the domain to be the set of all real numbers, the range we had the values of y greater than 5. Now for the inverse, the domain will be what it is going to have in x, what the original function had in y. So the domain will be values of x greater than 5. And for the range, okay, again, that's going to be the set of all real numbers. And just once more, okay, so just looking at what we have in the visual representation of that particular function. Okay, so you have for 3 to the x plus 5. Okay, we have again for this curve, which we have in red. Okay, so you have again like 3 to the 0 is 1. 1 plus 5 is 6, and we got 3 to the first is 3 plus 5 is 8. 3 to the second is 9 plus 5 is 14. 3 cubed is 27. 27 plus 5 is 32. So we have these respective ordered pairs. And swapping the x and the y values, okay, those will make up among the ordered pairs that define y is equal to the base 3 logarithm of the quantity of x minus 5. And again, both of the graphs will have symmetry with respect to the line y is equal to x. All right, now yesterday, okay, we looked at logarithmic bases with base 10 as well as the base e. And for what we have, just kind of like where we had left off last time, we cross over into the threshold of various capacities or contexts in which interest is applied. Okay, so just looking at what we have from page 378, and we have for the varying levels of compounding frequencies. So yeah, on page 378, okay, so we have with number 46. Okay, so we're working with the future value compound interest formula, where we have P times, okay, the quantity of 1 plus R over N raised to the N times T power. And now we have in this situation, we're looking for the future value. And for the various inputs, okay, so we're looking at the principal, or what is financed, okay, to be at $8,000. Now for the rate of interest, okay, that is at 3.5%. And converting to a non-percent decimal, okay, so you have like drop the percent sign, divide 3.5 by 100, so you have 0.035. And the time span, we're looking at 20 years. Okay. And if we're looking at the future value after 20 years, okay, say that we have in the first capacity, okay, if we're looking at annual compounding. So we have for annual compounding, so you have n is equal to 1. So you have with this formula, okay, so n is going to be at 1, and just putting in the values for a, or leading up to a, putting in the values PR as well as t. Okay, so P we have $8,000. You have times the quantity of 1 plus 0.035. Okay, now n is going to be at 1. Now for n times t, we have 1 times 20. Okay, now for the sum here, we have 1.035. And we have to the 20th. Again, to get to the result of 1.035 to the 20th, okay, you might have it as a y to the x or x to the y, second function or button, or you might have that looks like the arrowhead pointing upward symbol. And for 1.035 to the 20th, now that number is going to be just a little, slightly under 2. Okay, and so we have among the first digits, okay, we have 1.9897. And keeping the decimal and multiplying by $8,000. So the future value, we'll be looking at around $15,918 and 31 cents. All right. Now, so this is what we have in the case of annual compounding. So 15, 9, 18, 31. Okay. And if I up the frequency, going from annually to quarterly compounding, where we have it, n is equal to 4. Okay, so I'm still applying mostly the same numbers initially. So with n at 4, okay, so we have 1 plus 0.035 over 4, and this will be to the 4 times 20th power. Okay, now with 0.035 over 4 added to 1, now you're going to have the sum to get smaller, or to be smaller. So you have 1.00875. But now your exponent is going to be larger. We have not to the 20th degree, but to the 80th. And for this sum to the 80th power, okay, this number is now going to be just slightly over 2. And for the future value here, okay, we're looking at around $16,061.05. So again, for the same time, same input value monetarily, but changing the frequency. The more frequently the compounding is done, the higher the future balance is going to be. So you have a higher result going from annual to quarterly compounding, and we can anticipate the same thing yet with monthly compounding. For this time we are going to have n equal to 12. So for what we'll have here, say 0.035 over 12. We have raised to the 12 times 20th power. Okay, and so for what we have here. Okay, the sum, again, yet smaller. In fact, what's going to happen here is that we have 1.002916. We have 6's to repeat, and the exponent, okay, we have 12 times 20 is going to be at 240. So taking this number and raising to the 240th power, okay, so that number is going to be around 2.0117. And multiply by $8,000. So we have around $16,093.62. And in the case of daily compounding, okay, so we have an n at 365. Okay, so we got, so let's see. Okay, so we have with the numbers here. Okay, so you've got a small decimal with 0.035 to begin with. And once you're dividing by 365, I mean, it kind of comes down to adding like less than lint, okay, to 1. And for the power, okay, so we got 365 times 20. Okay, so you have virtually nothing added to 1, but it is the slightest trace. And for what we have here, so you have like a 1.0000958. And this is going to be taken to the 7,300th power. So you have a very small amount added to 1, but with this huge exponent, okay, there's going to be a bit of a compensation for this bit of scarcity that is added to 1. But once we take to this high power, okay, this turns out to be just even higher and above 2, so you have right at 2.01368 thereabouts, and multiply by $8,000. So we have for the grand total here, we have around 16,109.48. Okay. And then we have just kind of maxing out. If you could go beyond daily, okay, again, we have continuous compounding. Now, in terms of the value of n, now the author would say that it is not applicable, which in a way is true. If there's any other context upon which you could apply this, this would be just infinity. And for this statement, in determining the future value, again, as n approaches infinity, okay, this parenthetical statement becomes e to the r times t. So we got the continuous compounding formula. And so we have P, again, at $8,000. And for e to the r times t, so you have r, we have a 0.035. And t is going to be at 20. And 0.035 times 20, so this is going to be a 0.70. And for e to the 0.7, okay, so you have ever slightly more. So you have about a 2.01375. And so we have for the future value, okay, that's going to be right at 16,110.02. Okay, so just looking at what we have here. So again, starting out with $8,000, quoted percentage rate is at 3.5%, times for 20 years. And the more frequently the compounding is done, the higher the balance is going to be. So you have from annual to quarterly, okay, you have about like a $143 jump. Then going from quarterly to monthly, okay, you have about a $32 and some change jump. And you should go from monthly to daily. Okay, it's not quite so dramatic a change, about close to $16, but with daily you're very close to maxing out. And the jump from daily to continuously, again, that's about 54 cents. Okay, so you're once you get to continuous compounding, past daily, it's like you have a rate which is going to be increasing, then you meet a certain threshold, and then you have increasing at a decreasing rate. And concerning what we have with compounding of interest, and we have with the continuous, and this carries over to what we have for number 48. And for continuous compounding, once again we have A is equal to P times E to the R times T degree. And for the values that we're going to be treating, okay, so have P is equal to $6,000. And we have the time span is going to be 12 years. And for A, okay, so we have at 1% interest. At 1% interest, okay, so you have for R, okay, so you're going from percent to decimal, so R is going to be right at 0.01. And so for the future value, after 12 years, where interest is compounded continuously at 1%, okay, so that's $6,000. You have times E to the 0.01 times 12. So you have $6,000 times E to the 0.12. Again, E is that natural logarithmic exponential base number. And for E to the 0.12, again, E is that 2.718 figure. And for that to the 0.12 power, okay, so you have about a 1.127. And multiplied by $6,000. Okay, so we have right at 6,764.98. And so if I go out to 2% interest, okay, so R is going to be 0.02. And for the future value, okay, so same formula. So we're looking at $6,000. We have times E to the 0.02 times 12 And so you have $6,000 times e to the 0.24. And for e to the 0.24, okay, that number, okay, you have over 1.27. I'm just keeping this result and multiplying by $6,000. So we have here about $7,627.49. And for what we have in the case of part C, okay, so going from 1% to 2% and then out to 4.5%. Okay, so you have R, you have right at 0.045. Now for the future value, okay, so you have $6,000. You have times E, and for R times T, so you have 0.045 times 12. Okay, so you have $6,000 times E to the 0.54. And for e to the 0.54, okay, so that number, okay, you have just a little bit over 1.7. And multiplying by $6,000. Okay, so we're looking right at 10,296.04. And that'll be the result here. Okay, now for what we have in the case of interest. Okay, so this is once again compounding of interest. Now yesterday, okay, we looked at various contexts of interest, like between simple interest and compound interest. Now, in the case of number 49, okay, you have a simple interest and a compound of interest deal. And for what we have between the deals, okay, you have $10,000 that is borrowed, and we're looking at how much difference there's going to be interest-wise between the simple interest plan and what we have with the compounding of interest. Now, the simple interest plan has a higher percentage rate, and whereas the compound interest approach, okay, has a lower percentage rate, but the difference is virtually negligible. Now, for what we have in the case of what we're working with, okay, so we have initially, okay, what is being financed is $10,000. Okay, and for what we have now for the rate, yeah, we have at 5.5%. And as a decimal, so this is better 0.055. And the time span, okay, this is going to be for 4 years. Okay, now, this is with the simple interest plan. Okay, so for the simple interest, okay, so with simple interest, okay, so you have I is equal to PRT okay, so you have the principal, okay, so you have it $10,000. And for R, again, we have 0.055. And the time span we have for 4 years. And if I multiply the principal, the rate, and the time, okay, this will come out to $2,200. And that's going to be the amount of interest on this. So if someone were to borrow $10,000 and they went with this deal, 5.5% simple interest after 4 years, that person would pay back $12,200. Now, for the other plan, okay, for what we have in Part B, now the setup is where we have, again, you had the same amount financed. So we have $10,000. And the quoted percentage rate, okay, so you have it 5%. Whereas the decimal, we have it 0.05. And again, the time span is still going to be for 4 years. Okay. And now for this plan, you're looking at 5% compounded continuously. Okay, so you're looking for the future value. Okay, so if I'm looking for the future value, okay, so again we have A is equal to P times E raised to the R times T. So again we have for P, okay, so we have at $10,000. And you have times E raised to the 0.05 times 4. So you have $10,000 times E to the 0.2 and for this number, so for E to the 0.2, okay, that's going to be about 1.2214. And with the future value, okay, so we're looking at converting in terms of dollars and cents. Okay, so you have about 12,214.03. Okay, so you got this number. Notice we have with the 2,200, that was the amount of interest. Okay, now the 12,214.03, that is the future value. Now for the interest in this one, okay, you had the difference between the future value and what is financed. And guess what? For the amount of interest that would be accumulating, okay, we have right at $2,214.03. And in terms of how the numbers are going to compare, okay, so we got, again, with a simple interest plan, we had the interest accumulated to be at $2,200. And guess what? In spite of having the higher quoted percentage rate, we have nonetheless, in the context of applying simple interest as opposed to continuous compounding of interest, okay, that amount of interest is less than what we have with the continuous compounding at half a percentage point lower. Okay, and so for what we have in the case of the comparison question, it's going to turn out that the simple interest option turns out to be 1403 less than the other option. Okay, so whenever somebody talks about like interest and percentage rates, okay, you have to determine, okay, is this in the context of simple interest, or is it in the context of compounding, continuous or non-continuous? Okay, so again, 5.5% with simple interest with the time span and all as laid out turns out to be a cheaper route than the 5% compounded continuously. All right, now, and we'll look into other business applications, but now just going back to logarithms. Okay, and again, a logarithm by definition is the inverse of an exponential function. And for what we have regarding properties of logarithms. And the first one we sort of encountered when we went from an exponential function to one that is logarithmic. And in the case of the properties of logarithms, okay, so you have one here, okay. If you have a base A logarithm of a to the whatever power, we looked at y, but if you have, it doesn't matter what letter it is, but if you have a base A logarithm of a to the x, if the exponential and the logarithmic bases match, then the reduction is going to go with that which represents the exponent. In this case, you had the base A logarithm of a to the x is equal to x. And just kind of give you a visual in terms of how all this is going to play out. If I have something like, see, like with your calculator, if you have like log of 100, again, just log by itself is going to make reference to a base 10 logarithm. So you have the base 10 logarithm of 100. Now looking at the logarithmic base 10 and what we have with 100. Now 100 is a multiple of 10, and it is also going to be an exponential power of 10, or in this case an integer power. So 100 in terms of base 10, okay, this is going to be 10 raised to the second. So here we have a is going to be at 10, x is going to be 2. So the base 10 logarithm of 100 reduces to 2. And with our other key in the scientific calculator regarding logarithms, so we have ln. Now if I'm looking at the natural logarithm of e to the negative 4, in context, that is going to be a base e logarithm of e to the negative 4. So we have with this layout, a is represented by e, whereas in the case of x, that is going to be represented by negative 4. So we have the natural logarithm of e to the negative 4 to become negative 4. And let's say that for something that we don't have in many a calculator, you have a base other than natural or base 10. Now let's say if I have a base 5 logarithm of 125. Here I can reduce, because like 10 is to 100. Well, guess what? 5 will be to 125, in the sense that the higher number is going to be both a multiple and an integer power of the logarithmic base number. And for 125 is going to be 5 raised to the third power. Since they have like 5 times 5 times 5 is 125. And here we have a is represented by 5, x by 3. So this reduction amounts to the number 3. Okay, and we have, so this is our first property. And we have next, okay, something that is akin to it. And it might be a while before you see this one again until we get to logarithmic equations. Now for a to the base a logarithm of x, we have another scenario where you have a match between the exponential base and the logarithmic base. And this is also going to reduce to x. And just some examples here. If I have, let's say something like 2 to the base 2 logarithm of 5. Okay, so a is going to be at 2. X we have at 5. And guess what? This reduces to x. And what is x? Well, x is going to be at 5. Now let's say if I have, going back to the number 10. Say if I have 10 times, okay, the base 10 logarithm of 2. Or 10 to the log of 2. So again, with log, this is going to be referencing base 10 logarithm. So 10 to the base 10 logarithm of 2, that is going to go to 2. And we can say that with the number e. So if I have something like e to the natural logarithm of 10, okay, so this is going to go to, now natural logarithm is going to be a base e logarithm. So e to the base e logarithm of 10, think of like a as being represented by e, and x is represented by 10, and that is going to be the ultimate result here. All right. Now again, your calculator is going to have natural and base 10 logarithms, and where we can get to certain decimal values if we don't attain an integer result or rational number in the process. And let's say if you've got different bases to deal with, and you're trying to configure a value, well, we have what's regarded as a change of base formula. And for the change of base formula, okay, for what we're going to have to occur in the change of base formula, okay, so you have base a logarithm. And say we have of m. Okay, so you don't have a match between the exponential or the logarithmic base. You could, but we'll just say that if you don't, what you can do is that you can write what we have here in terms of another logarithmic base. Okay, so we have like a base b logarithm. And for the base a logarithm of m, okay, we'll have a ratio which we'll have as base b logarithm of m over the base b logarithm of the variable that was originally the logarithmic base. So you have the base b logarithm of m all over the base b logarithm of a. And just to kind of give you a bit of an example, in just a moment, okay, so I had the base b logarithm of m over the base b logarithm of a. And with your calculator now, the base b logarithm, you could choose to go with the natural logarithm and have that as the natural logarithm of m all over the natural logarithm of a. Or you can go with the base 10 logarithm of m all over the base 10 logarithm of a. So you could use either one, okay? And you'll still come out to the same reduction. And show you how this would play out. If I have something like a base 3 logarithm of 17, so if I have a base 3 logarithm of 17, okay, so m is represented by 17, a is represented by 3. And for the base b logarithm, I can choose either natural or base 10 logarithms. I'll just go with ln on this one. So I have ln of 17 over ln of 3. And in terms of, say, just like a calculator display, for some models, okay, so you have ln of 17 and you have /, and you have to hit ln or enter ln again. So you can't take it like natural logarithm of 17/3. You would get a wrong answer. So you had to put in natural logarithm twice, that of 17 over the natural logarithm of 3. And for the decimal approximation, okay, this will come out to just a little bit under 2.6, and to the nearest 3 decimal places, this will be about 2.579. Now, let's say if you have a decimal number for the logarithmic base. So you have the base 1/2 logarithm of 20. And again, you could reapply natural logarithms, but we'll go with the base 10 logarithm on this one. So here we have a is represented by 1/2, m by 20. So here you can say I have the base 10 logarithm of 20 all over the base 10 logarithm of 1/2. Okay, so you have, again, the base 10 logarithm of 20 over the base 10 logarithm of 1/2. And for this reduction, now we're going to have a negative value. And say to about the nearest 3 decimal places, this is going to come out to about negative 4.322. All right. So we have among the introductory properties that we have concerning logarithms. Again, so you have base a logarithm of a to the x goes to x, and a to the base a logarithm of x goes to x. And again, we have the change of base formula. And now there is another property. Now for this first one, you had a match between the exponential and the logarithmic bases. But say if you're looking at reducing a term where you don't have quite the convenience of a perfect match between the exponential and the logarithmic bases. So again, just kind of showing a little bit of a contrast. So you have a base a logarithm of a to the x goes to x. Let's say for the next property, if we have something like base a logarithm, and we say you have of m to the r. Okay, so you have distinct variables in the bases. So we had the base a logarithm. Now the exponential base is going to be m. Now the exponent, we're going to have it r. And if this were to be written in any other way, the exponent can be written as a coefficient. In this case, we can say we have r times the base a logarithm of m. So the base a logarithm of m to the r is equal to r times the base a logarithm of m. And just to kind of show you Okay, just how some of these situations are going to arise. Say if I have something like base 3 logarithm, 5 to the t. So a is at 3, m is at 5, and we have r at t. And if I write the exponent as a coefficient, I can say that I have t times the base 3 logarithm of 5. And let's say that if I have something like the base 2 logarithm of the quantity of x plus 4 raised to the third power, x plus 4 quantity to the third power. So you have a is represented by 2, m is represented by the binomial x plus 4, and r is represented by 3. So if I write in this formation, putting that which represents r at the front, so we have 3 times the base 2 logarithm of the quantity of x plus 4. Okay, so you have in the attachment of the base 2 logarithmic term, x plus 4, the whole binomial is an attachment, so we need parentheses. And also another, it's a little bit of a tricky item, but also stressing the parentheses. Now before we had the exponential base as a two-term expression. But let's say if I had a two-term expression for the exponent. And say if I have the base, let's say we have a base 5 logarithm. Now say we have of t raised to the y plus 4. So you have a base 5 logarithm of t raised to the y plus 4. So a is represented by 5, m by t, and r is represented by y plus 4. So if I reconfigure, okay, now r, again we have y plus 4, and we have times base a logarithm, which we had to be the base 5 logarithm, and we have of m, which we happen to have at t. Now this is where you had to be careful, because the base 5 logarithm of t is going to be multiplied by y plus 4. And if I do not include parentheses here, it's going to read, the output is going to read it like you have y separately, and where y would be adding to separately 4 times the base 5 logarithm of t. So like in Alex, let's say, if I were to enter this as what I have on the screen right now, it would read it as if you have just 4 multiplying the base 5 logarithm of t, whereas you also need y to be multiplying that logarithmic expression. And so you'll need parentheses here, so just stress that you're having y plus 4 to multiply the base 5 logarithm of t. Again, just stressing, okay, so you need the parentheses. Alright, and we have, in terms of these individual items, okay, so these are various layouts of what we have for single logarithmic terms. Well, let's say if we have interactions between distinct logarithmic terms in the same base. And what I mean by this is we're going to have, after what we have in the first round of the properties of logarithmic terms, this is going to cross over to what we have with sums and differences of logarithms. Okay, so for what we have in the case of sums and differences of logarithms, Okay, so for sums and differences of logarithms, okay, you have, say if I have a base A logarithm of two factors in the attachment where we have m and n and they are multiplying each other. Okay, we have the base A logarithm of m times n. Now you're going to have multiplication to imply addition. So I can split up this expression as two separate base A logarithmic terms. We're going to have the base A logarithm of m plus the base A logarithm of n. So multiplication in the attachment implies addition of separate logarithmic terms in the same base. Now, if I have, say, where the difference will come in, this is going to originate from taking, say, the base A logarithm of m divided by n, and here, upon separating, division is going to imply subtraction. So this will come down to the base A logarithm of m minus the base A logarithm of n. And I'll mention now the converse is going to ring true. So if I have a sum of logarithmic terms in the same base, now I'm looking at uniting separate logarithmic terms in the same base. Now addition is going to imply multiplication of the attachments. Same thing here. For the difference of logarithmic terms, this will imply division between the attachments. Okay, and you're going to have at the top the attachment of the positive logarithmic term, and at the bottom of the ratio will be the attachment that was in reference to the negative base A logarithmic term. So m is going to be at the top, whereas n is going to be on the bottom. And let me just give you just a couple of quick samples here. Okay, say if I'm looking at expressing as sums or differences of logarithms. While converting exponents to coefficients. Okay. I'll say just first of all, okay, just kind of here's a bit of an introductory example. Okay, so if I have the base 3 logarithm of a times b. Okay, so I have like a is represented by 3, m times n is represented by a times b. So upon splitting up, we're going to have the base 3 logarithm of a plus the base 3 logarithm of b. Now let's say if I have, say the base 3 logarithm of u to the second times v to the fourth. Okay, so if I split up, right now I have the base 3 logarithm of u to the second, and we have plus the base 3 logarithm of v to the fourth. And Now just stressing, okay, we have converting exponents to coefficients. You got your exponents with 2 for u and 4 for v. And so in the rewrite, we're going to have 2 times the base 3 logarithm of u plus 4 times, okay, the base 3 logarithm of v. Now here's another one. Okay, it's going to be a little bit different, but not drastically different. Let's say if I have something like, we'll say, I'm working with base 3. If I work with base 5, say if I had the base 5 logarithm of 25 times x to the 9th. Okay, so you got factors in the attachment with 25 and x to the 9th. Okay, so you got the base 5 logarithm of 25, and I have plus the base 5 logarithm of x to the 9th. Okay, now I'm going to rewrite the 9 as a coefficient, but just with the base 5 logarithm of 25. Now you don't see an exponent attached to 25, but something to notice, kind of like in terms of the earlier reductions, like in the first property of logarithms. 25 is like the 125 relative to 5. Well, 25 is both a multiple and an integer power of 5. And if you notice, okay, the base 5 logarithm of 5 to the 2nd, guess what? That's going to go to the power, which is 2. And in the case of the base 5 logarithm of x to the 9th, that 9 is going to be a coefficient. So in this expansion, I'm going to have 2 plus 9 times the base 5 logarithm of x. And so just remaining item here. If I have, let's say, the base 2 logarithm of 4 over b to the 3rd. So here I'm going to have a base 2 logarithm of 4 minus, okay, the base 2 logarithm of b to the 3rd. Again, if you notice, 4 is to 2, kind of like how 25 was to 5 just a moment ago, because you have 4 is both a multiple of 2 as well as an integer power of 2. So 4 is going to be 2 squared. Now for the second term, I can make the 3 into a coefficient. So the base 2 logarithm of 4, that is going to go to 2. And we have minus, and we've got 3 times the base 2 logarithm of b. Now let's say if we have simultaneous multiplying and dividing. And we'll say we have base 4 logarithm, and say we have 15 a to the 3rd, say b to the 2nd over 64 d to the 5th. Okay, so I got really 3 factors in the numerator, 2 in the denominator. Okay, so if we look at expanding, so I'm going to work with what's at the top first. So you have the base 4 logarithm of 15 and I have plus the base 4 logarithm of a to the third, and I have plus the base 4 logarithm of b to the second. Now with both 64 and d to the fifth on the bottom, we're going to subtract what we have here. So we have minus the base 4 logarithm of 64 minus the base 4 logarithm of d to the fifth. Okay, and if you notice with the first term, okay, 15 is not even a multiple or integer power of 4. So that is already in simplified terms. Now for the base 4 logarithm of a to the third, we can write this as 3 times the base 4 logarithm of a. Next term, we can convert the 2 as a coefficient, where we have 2 times the base 4 logarithm of b. Now for the base 4 logarithm of 64. Now, unlike 15, okay, now 64 is both a multiple and an integer power of 4, because 64 is going to be 4 to the third, and we'll convert that shortly. For the last term, go ahead and write this as minus 5 times the base 4 logarithm of d. Okay, so having for the final dismount, so you had the base 4 logarithm of 15 plus 3 times the base 4 logarithm of a plus 2 times the base 4 logarithm of b. And then we have with the term that follows, okay, we can say we have minus 3. And we have minus, once again, 5 times the base 4 logarithm of d. Okay, so that will be the final answer in terms of expanding.